In this video, I want to take a look at solving a non-homogeneous second-order differential equation with constant coefficients using the method of um, undetermined coefficients. There's two methods that I always mix the names up, which is why I had to hesitate there. Anyway, in class we did an example where the thing over on the right-hand side of the equation here was a polynomial. In this video, I want to do an exponential. So I've got my second order homogeneous equation. In order to find the general solution, I need to first solve the homogeneous equation, find the general solution for that. So that corresponds to assuming that the answer looks like y equals e to the rt, plugging it in, getting this polynomial equation here, solving for r to be r2 and r equals 2, r equals 3. And so the homogeneous solution, the general solution to the homogeneous equation, I should say, the general solution to the homogeneous equation looks like some constant times e to the 2t plus another constant times e to the 3t. Pick your constants and you've got different solutions. Okay. Now, I need to find a particular solution to the given differential equation, to this one. Okay. Now, since this is an e to the 5t over here, I'm going to guess that my particular solution looks kind of like e to the 5t. So I'm going to guess a times e to the 5t and see if I can find a value for a. If I can't, then I have to take a different guess. Right? Let's see what happens though. If I take yp equals e to the 5t, the derivative would be 5 e to the 5t, the second derivative would be 25 e to the 5t. Plugging this into the equation, there's the second derivative minus 5 times the first derivative plus 6 times the function itself, which is supposed to be equal to e to the 5t. Now let's simplify it. Combining like terms over here, like they're all like terms, I've got 25 minus 25 plus 6. Each of those are times a. Anyway, so I end up with 6a e to the 5t leads to equal e to the 5t. Well, looks like a needs to be 1/6. So y sub p is going to be 1/6 e to the 5t. If there was no a that worked, I'd end up with something really screwy here. I'd end up with, 1 equals 0 or whatever, something that's just not possible. And so there'd be no solutions for a, and I'd have to go take a different guess. But generally, if you got an exponential here, then it's pretty good chance that something times that exponential will be the particular solution. Once you have the particular solution, of course, you can write down the general solution being that one particular solution plus the general solution to the homogeneous equation. Okay. Now, I say usually, but what could go wrong? Well, consider this. This equation is the same as the last one on the left, except that I've got a different g over here on the right. So solving the homogeneous equation is the same as before. You're going to have an e to the 2t and an e to the 3t. The problem is here now, what I want to guess is an a e to the 2t for my particular solution. But that just isn't going to work because e to the 2t is part of the homogeneous equation, right? The solution for the homogeneous equation. So if I plug an e to the 2t in over here, I'm not going to get an e to the 2t out of here. I'm going to get 0. So I got to do something else. So what I'm going to do is I'm going to multiply by t, and I'm going to try t e to the 2t. That doesn't work. I'm going to try t squared e to the 2t. That doesn't work. Probably t cubed. Eventually it should work. And why it works we'll look at in the next section, so next week. But here we go. If I take a guess like this, the derivative looks like, I got to do a product rule here, so derivative, so I'm doing a times t is my first and e to the 2t is the second. So derivative of the first times the second plus the first times the derivative of the second. Anyway, factor out the e to the 2t, it looks like this. And then the second derivative, again, you got to do a product rule on that thing. And factor out the e to the t, and I get this. Plugging all this in, there's the second derivative minus 5 times the first derivative plus 6 times the function. That's supposed to equal e to the 2t. Now I look at this and I say this could have issues because I'm seeing, when I distribute each of these in, I'm seeing a constant times e to the 2t, but I'm also seeing a constant times t e to the 2t, and I don't have any t e to the 2t's here. So if I end up with any t e to the 2t's left over here, then this isn't going to work. It's going to, then the coefficient in front of it would have to be 0. But we'll see here what happens. I think the t e to the 2t's actually go away. So combining all my like terms, my constants here are 4 and minus 5a, and then the things times t, there'd be a 4a times t, there'd be a minus 10a times t, and there's a plus 6a times t. When I combine all those together, it looks like just 0, and I end up with, hey, minus a e to the 2t equals e to the 2t. So a has to equal minus 1, and my general solution looks like this. Okay. Why do you just multiply by t? Well, as I said, next week we'll look at another method for solving these problems that's more general. These are very specific. This method of undetermined coefficients is very specific. When the thing over here is a polynomial, you're going to guess a polynomial. When the thing over here is an exponential, you're going to guess an exponential. Unless, of course, that exponential is part of the homogeneous solution, in which case you're going to multiply by t or t squared. If it's a sum of sines and cosines, or just one sine or one cosine, then I'm going to guess a sum of sines and cosines. So I'd guess like an a sine plus b cosine, and the argument inside the sine and the cosine would be whatever it is already in G. Anyway, there's some examples like that in the book. You should try some of these for homework, and we will see you all on Monday.